Okay, in this problem, we're going to look at another problem where we're asked to find distance between a couple of things in three-dimensional space. And it doesn't tell us what these things are. So at this point, you should be starting to be familiar enough with notation and the standard form of things that you should recognize for sure that this last equation here is the equation of a plane. It's in that standard form, ax plus by plus cz equals d. So this is a plane in R3. The first equation, sometimes that takes students a little bit of time to recognize that that is also the equation of a plane. It's just got the y term isolated. So if you look at the equation over here that I labeled plane that you probably recognized as the equation of a plane, and this one, you can think about that you could just add or subtract some terms to one side of the equation or the other and get this equation in this same standard form as the other equation of a plane. So this is also a plane. I'm going to rearrange it so that it is in this form. We'll use some features of that form to help us with some vectors that we're going to need. So this one is also an equation of a plane. I could subtract 2x and z from both sides of the equation, or I'm going to just subtract y from both sides of the equation, just one less step there, to put that in that standard form. So 0 equals 2x minus y plus z, also the equation of a plane. Okay, so we are supposed to find the distance between two planes here. So one thing that we might just think about is kind of planes in three-dimensional space and how those planes might be with each other. And so if I have two planes, there's really three possibilities for how those planes could be oriented with respect to each other in three-dimensional space. So one is they could be the same plane. If these two were the same plane, then the equation would be the same equation. You might notice that on the side where I have all the variables, it's the right side on this one and the left side on this one, that all those coefficients are multiples of each other. But if I multiply this equation through by 2, I do not get the same term on the constant side. So these are not the same plane, or they would be the same equation. I could rearrange them as long as I'm using valid algebra, but they would be the same equation. So they could be the same plane. That's not the case here. They could be parallel planes that do not intersect. Or if they're not parallel planes, then if you extend them far enough out, they would intersect each other at some point. So if they intersect each other, the distance between them would be 0 eventually if they intersect each other. So somehow implied in this problem is the fact that these two planes do not intersect each other. They're parallel planes. Even if they didn't tell us that, we could tell that from these equations, that these two planes are parallel to each other. So one way we could tell that these two planes would be parallel to each other is to think about vectors that are perpendicular, or I'm going to use n for normal, to each of these planes. So for this plane that I have here with 0 on one side, a vector normal to that plane is 2, negative 1, 1. So we're using that same trick of pulling out those coefficients and thinking about how we derive the equation of a plane and then going backwards from that, that would give us the components of a vector perpendicular to that plane. If I do the same thing for this other plane over here, let me call this one n1 and this one n2. I get 4, negative 2, 2. And you'll notice that these two vectors are scalar multiples of each other. So because these two vectors are scalar multiples of each other, those two vectors are in the same direction. They have different magnitudes, but they're in the same direction. They're parallel to each other. And if those two vectors that are perpendicular to these two planes are parallel to each other, then the two planes will be parallel to each other as well. So noticing that these two vectors are scalar multiples of each other helps me understand that these two planes are parallel planes. All right, so thinking about the fact that these two planes are parallel planes and that I want to find the distance between those two planes. So again, you can memorize a formula, or you can kind of just think through the geometry using what we know about distances, right triangles, vectors, points, things like that. All right, so I have two planes. I've got vectors perpendicular to either plane. Those vectors actually are perpendicular to both planes. They're scalar multiples of each other, so they're in the same direction, just different lengths. And what I want to find is the distance between those two planes. All right, so I've got vectors perpendicular to either plane. I could move that around and it would be perpendicular to that plane. I can easily find a point on either plane. I'm just going to put a point here and call that A. And then this should look a lot like a previous example that we looked at, where we were finding the distance from a point to a plane. So the distance from this point to the plane is the same as the distance between these two parallel planes. So we did this before. We had a distance from a point to another plane. So hopefully at that point that connects back to something that you've done before, and from there it's not too hard. I'm going to go ahead and talk through what we did before. We found another point on the other plane, so I'll find a point on one plane, another point on the other plane, I'll call that one B. We found a vector between those 2 points, so I think I called that BA before, right? And then I've got my N vector that is perpendicular to either of these planes, but I have it oriented here. And what I want to find is this distance here, which is the same as this distance here, which is the adjacent side of that right triangle. And so thinking about the labeling that right triangle in terms of dot products and cross products, that would be the dot product here. So that distance would be the absolute value of the dot product of the vector BA with N divided by the magnitude of the vector you're projecting onto on that adjacent side. So that would be the magnitude of N. All right, so I just need some vectors on my 2 planes here, or some points on my 2 planes here, and then just do my calculations with my vectors. Doesn't really matter which vector I call, or which plane I use, that I have a point called A and a point called B. This is just a generic representation of this situation. So I'm just going to write down a point on this plane. I can use either of these equations of this plane to get a point on this plane. I'm just going to use this first one, maybe. So if, say, x is 0 and z is, say, 1, then I have a point 0, 1, 1. Again, there are infinitely many points. As long as it makes this equation true, then that would be a point on that plane. I need a point on the other plane, so I'll call that one B. And again, infinitely many combinations of x, y, z coordinates that would work and make this equation true. I'm going to choose x is 0, y is 0, and z is 1/2. Would make that equation true. Okay, so now I just need my vector BA. Right, so if I start at B and end in A, the change in x is 0, the change in y is +1, and the change in z is +1/2. I've got my n vector. I could actually use either of these for my n vector. Remember that I'm really interested in the direction here, not necessarily the magnitude, although I do need to make a choice because depending on which one I use, I will need to use the right one to divide by my magnitude here. So I'm just going to use this one, a little bit smaller numbers to work with here. All right, so let's do the dot product here, BA dot N1. So our dot product, 2 times 0 is 0, -1 times 1 is 1, and 1 times 1/2 is 1/2, so -1/2. The magnitude of N1, so we will have square root of 2 squared is 4, plus -1 squared is 1, plus 1 squared is 1, so square root of 6. And then I can use my formula that I figured out here from just labeling the picture to find that distance. So I'll need to remember to take the absolute value. Remember, distance should not ever be negative. So absolute value of -1/2, so I'll have 1/2 divided by square root of 6. Probably not a good idea to leave a fraction within a fraction. That's not a very tidy way to write your answer. So you could write that as 1/2 square root of 6 if you really love to rationalize denominators. You could go ahead and do that as well, but I would probably leave it just like that. So again, just thinking through the geometry, being able to draw a generic picture, thinking about sides of a right triangle, dot product and cross product for helping you to label those distances along those sides of that right triangle, rather than memorizing a problem or a particular formula that's just specific to a very specific type of problem. Much better way to think about managing all of the formulas in this chapter.